and didn't think that it was important, sold the book back for beer. It was super important. And I remember coming to grad school and my friend would say, think of a matrix. I'm like, nothing's coming up. Nothing at all. Sorry.
I'm a switch. Thank you.
Power sets, your favorite thing. I learned from your midterm, this is your favorite thing. So if somebody asks you something sigma algebra, you have to go through the definitions, like the checks. So the first thing is the whole set and the power set. Sam, what do you think? Is the whole set and the power sets?
The whole set of
Like if I take the power sets of ABC and you had to write them, list them out, would the ABC itself be in there?
yes.
Proof by Sam.
Can I use that on my homework?
No. Why is it in there?
Definition.
Definition of power set, like all the subsets of ABC, even the proper one, non-proper ones are in there. And because all possible subsets are in the power set, including omega, which is a proper subset of itself. Second question. So we're done here. Done there. I like to do the easy ones first. Second one. If A belongs to the power set, does the complement of A belong to the power set? So?
Yes.
Relative to the omega, right? So the power sets are just all subsets. So we got one no and one yes. Huh? Yeah, omega is your whole world. You set that up, it is your whole world. So you start with omega, set it up, all right? So then we're gonna go with yes. Give me an example of one subset that's in there. Just a little singleton A. What's the complement of A? That's true. I saved the best for last. Number 3 is always the worst. For metric spaces, number 3 is the triangle inequality. I always save that one for last. For this one, it's the countable unions. Got all, Isaac? All right, so let's go to number 3. I made you guys do this, actually. How many will there be? There's 3 elements in there. We did this with combinatorics. Huh? You know, it's supposed to keep going, but it's not going to keep going. There's going to be a last one. How many will I have? Do you remember? You guys had to do something with this on. I think I proved this for you. If you have 3 elements in a set, how many power sets will you get?
Third.
8. Not that it matters, but there's not an infinite number. The worst I can get is 8, right? There's 8 total subsets. Empty set, the whole set, and then all combinations of the A, B, C that you could possibly have. So is it true that if I take some combinations of subsets and I union them, let me write it this way. We don't have to have infinite stuff. If I took a whole bunch of sets and just union them up, are they still going to be in there? Give me an example. Give me an example of one subset. That's your favorite one. Give me a more complicated one here. Yes. Sigma algebra. Okay, I want to do the next one on Wednesday because it's a little bit longer and tougher to understand. I wish I had seen these things when I was in graduate school because they just slapped up upside the head on the first day and gave us complicated things. So you work with sets. That's why foundations usually starts with sets and discrete math starts with sets, because in all of pure mathematics, you need sets. This is just a definition of sigma, something called a sigma algebra. It comes from actually probability. So the omega's a sample space, and these sets are events. And so it's building up probability theory, but it's also used in partial differential equations of all places. It's used in all kinds of areas. So what's going to happen is on this sigma algebra, I'm going to define something called a measure. And that measure, it's in probability, it's called a probability measure. And we just called it a measure. So I was not in probability. And once you have that measure, you can define a new way to integrate that's not Riemann. Called the Lebesgue integral. So I'm going to take you all the way up to the Lebesgue integral in our class. The Lebesgue integral integrates things that the Riemann integral can't, and that we care about in places like PDEs. I used it for PDEs. Colonel Clark can give you where they use in statistics and probability. but it's used all over the place. So when I first got to grad school, everybody's talking about Lebesgue integration, Lebesgue integration. Like, I don't know what that is. I have no idea what you're talking about. So I made the mistake of going to my Swiss German partial differential equations professor and asking him what a Lebesgue integral was. And he just held his hand on his forehead and he said, "You don't know what that is? I learned that when I was 15. Like, I don't know what that is. I'm never asking him a question again. So then I just asked other grad students, but it turns out in Europe, they'll learn this a lot earlier than us. So he didn't learn it at 15, but probably a lot earlier than us. I wasn't going to go back there and say anything to him. This is a guy that would tell us that you can have an oral exam at the end of the semester, because I'll give you an oral, you automatically get a B for being in my class. If you want an A, you can take an oral exam, but I reserve the right to give you a C. A C is an F in grad school. And I thought, well, I first went and found out, did he ever give someone a C? Like, if you go in there and you're brave enough to go in there, will he give you the A? He gave someone a C. Yeah, I wasn't going to him again for any more sense. All right, so that's where we're leading. We're leading up to the Lebesgue integral. It's kind of cool. You'll get out of undergrad knowing what that is. So I really thought about how to play it out. So any questions?
Ma'am, did you end up doing your?
I did. And he ended up like tearing me apart and asking me to prove the mean value theorem from calculus. And I wasn't there. Like, I had my prepared notes, like, I don't know if I can prove the mean value theorem, but he gave me the A. I left crying, but I got the A.